If you were designing an eye, here are your choices. The first option is a single receptor. All you need is a photosensitive cell. As light reaches it, the light is changed, transduced into electricity. This is how your porch light knows when to come on at night. During the day, it sees that the light is present and keeps the switch in an open position. When the sun stops shining brightly, luminance is low, the switch turns the porch light on. The advantage of this approach is that it is a simple system. The disadvantage is that it can only determine the overall amount of light. The receptor can't tell where the light comes from. There's no direction information. There's no way to know if the light is in front of you, behind you, near or far. You can improve this design by having multiple sensors, but they still don't provide much information about the directionality of light. It would be better if you could exclude all light, except rays which come from a particular direction. Thus the invention of eye cups. This was all the rage 500 million years ago or so. Very stylish. The eye cup encircles the receptor and extends outward. Only light that makes it into the tube of the cup will hit the photoreceptor. Depending on the depth of the cup, the receptor can be quite directional. A takeoff on eye cups was to put pigmented cells behind the receptor. Light that misses the receptor won't bounce back up. The eye cup with pigmented cells had much less halo effects on their image. A third alternative is to bundle a lot of eye cups together. This design is called a compound eye. Each segment, called an immodum, can operate independently, but they don't work together very well. While in vogue 300 million years ago, the design is still popular with many insects. You get a very wide field of view, but you can't see very far. This is Mr. Magoo vision. Each receptor produces a dot, so the combined image of all the dots is like an old newspaper photo, or an image of a dot matrix printer. This works if you're a bumblebee, but explains why they keep running into things. They can see at 1 foot what you see at 60 feet. Instead of 20/20, they would be 20/1200, blind by any human standard. The fourth approach uses an array of photoreceptors and a single light source. It's the design you played with at summer camp, the pinhole camera. You take a cardboard box, make a tiny hole with a pin on one side of the box, and an image is projected on the opposite side. The image is upside down, but is very sharp in detail. You can't adjust the focus, but in high light conditions you don't need to. If you have plenty of light, you'll get good pictures. Essentially, this is a conversion of how flatworms see. The eye cup is enclosed, leaving only a tiny pinhole entry. This is the type of eye used by the nautilus, a sort of squid in a shell. There's a single input source, the tiny pinhole, and the image is projected onto multiple photoreceptors. Since there is an array of receptors, the image is represented by a set of outputs. Of course, an even better design is to fill the pinhole with a lens. This is the plan vertebrates and octopi use. Instead of a single ray through a narrow hole, the lens bends the light. This refraction of light focuses the rays on the array of receptors. Each beam of light focuses on a specific receptor. And if the lens can change its shape to bend more or less, you can change the focus for near or far images. Building on this basic design, the human eye has receptors for low light conditions and a separate set of receptors for high intensity conditions. It is also able to see colors. In addition, humans have a complex system of neural outputs, analyzing centers, and specialized projection areas. All in all, we chose the best design.